Hi, I'm Jessica Cleghorn, and I will be discussing my summer research project, Modeling Molecular Transformations in Highly Polar Complexes. Chlorofluorocarbons, also known as CFCs, are volatile synthetic compounds of carbon, chlorine, and fluorine, and have been the subject of intensive research in the atmospheric sciences due to their atmospheric ozone-depleting properties, contributions to global warming, and relatively long atmospheric lifetimes. In this work, we plan to investigate a complex reaction involving an alkali metal to determine how the charge transfer from an electron donor would influence the process. Specifically, we are interested in exploring the effects that molecule compression would have when attempting to form F3C2Cl3 by framing lithium and trichloromethyl counterions so that they attract one another across the molecule trapped in between. The calculations for the series of systems were carried out using consistent ab initio calculations at the MP2 level of theory with extensive basis sets. We first studied the trifluoromethyl and hexachloroethane system in the absence of an alkali metal atom to determine if the expected products would form and to have a baseline to compare to once the alkali metal was added to the reaction. The reaction barriers for all systems were gradually scanned by continuously reducing and fixing the distance between carbon atoms of both molecules and observing the relative alterations in both geometry and energy. We are interested in determining the barrier top and ultimately the height of the energy barriers, or activation energies, relative to the starting material. Using the data obtained, energy diagrams for each system were constructed. A comparison between the systems would allow for the determination as to whether the initial expectations were correct and the barrier was indeed lower than for the systems without an alkali metal. The results indicated that the addition of lithium alters the reaction products and allows for the attachment of trifluoromethyl, forming a new carbon-carbon bond without breaking the original one. It was suggested that this could have occurred because the ionization energy of lithium was not low enough, meaning the electron was not able to transfer sufficiently. To try and remedy this, the system was evaluated with a substitution of cesium for lithium, as it is a larger atom with a lower ionization energy. However, the same outcome was achieved. Upon further reflection, since the F3C2Cl3 product is likely to be an undesirable species, these results provide an alternative path to hindering and/or potentially blocking its formation. In the end, we remain with the available comparison, where the two energy diagrams show that the barrier for the trifluoromethyl and hexachloroethane reaction drops considerably by about 1 electron volt when lithium is added behind trifluoromethyl. Overall, this investigation has provided more information about these systems and can be used to help predict and monitor the overall system evolution if carried out experimentally. Thank you.